purpose of these videos here and all the other ones in the module is to provide worked through answers for you for the worksheets. So if you haven't done the worksheets, then there's absolutely no point in watching these videos. So if that's you, I strongly suggest that you pop on back, try the worksheets. If you can't do the worksheets, you can come to these videos, or you can go ahead and actually watch the movies within the module. On the other hand, if you've just got a couple of questions that you couldn't understand, then that's the time to come back to these movies and work your way through them. Hope that makes sense. So when talking about atomic structure at GCSE or A-level, one starts off talking about the nucleus and the particular subatomic particles, protons, neutrons, and electrons. You need to know the relative masses of these. You need to know the relative charges of these. You need to know that the number of protons in an atom is the atomic number, and that defines the properties of that atom, not so much because of the number of protons, but because of the number of electrons. You also need to know that the mass of an atom, unless you're a nuclear chemist, which we call the mass number, is simply the number of protons, each of which of course weighs 1, plus the number of neutrons, each of which weighs 1. So let's go through these various possible answers. Neutrons and electrons have approximately the same mass. Now, as protons and neutrons have the same mass, so we can eliminate that one. Atomic number represents the number of neutrons. No, it represents the number of protons, so we can eliminate that one. Number of electrons, the same as the number of protons in a neutral atom. Oh, I like that idea, so let's give that a little tick. Number of electrons, same as the number of neutrons. No, we've already said the electrons is the same as the number of protons. And number of neutrons is the same as the number of protons. No, we've already decided that the equal numbers are of protons and electrons. Always good, by the way, in multiple choice, even if you think you've got the right answer, to keep looking at all the possible answers. Anyway, C, fairly straightforward there. How many of each of the subatomic particles contain in atom 110 CD? Well, we look on the periodic table, we find cadmium at element number 48. Now, the fact that it's at 48 immediately tells us the atomic number, which of course is the number of protons. So without further ado, we can eliminate answers B and C. Okay. Then we look at the mass number, this 110 up there. That's the number of protons plus the number of neutrons. We already know the number of protons is 48, so therefore the number of neutrons is 110 minus 48, which is 62. So we're looking for something that has 48 protons, 48 electrons, and 62 neutrons. And of course, it's answer E. So this particular question, the wording can be a little bit confusing. So let's think our way through it. In which of these pairs, well, there's a pair, there's a pair, and there's a pair, do the atoms have the same number of neutrons? So what we're going to have to do is we're going to have to look at each members of a pair. So start off with hydrogen 3 and lithium 6, figure out the number of neutrons in each and compare them. So we'll start off with 1, hydrogen. There's hydrogen on the periodic table. It's got an atomic number of 1, so that's 1 proton. This 3 is, of course, the mass of this particular isotope, this particular atom. So therefore, the number of neutrons is 3, which is the total of protons, and neutrons minus 1, number of protons, which is 2 neutrons. So hydrogen 3 has 2 neutrons. Lithium 6, lithium starts off atomic number of 3, so that means 3 protons. 6 minus 3 is equal to 3 neutrons, so therefore these do not have the same number of neutrons. Hydrogen 3 has 2, lithium 6 has 3. So hopefully I went through that slowly enough. Everybody is with me because I'm going to speed up a little bit with the next ones. Carbon 14, carbon has 6 protons, so therefore carbon 14 has 8 neutrons. Nitrogen 15, nitrogen has 7 protons, so therefore nitrogen 15 has 15 minus 7, or 8 neutrons. And look at that, those two atoms in the pair have the same number of neutrons. So we've got at least 2, so we can eliminate A because 1 didn't have it. We can eliminate E because pair number 2 has got it, and we can eliminate D because we found that 2 has, and that implies that only 3 has. So what we've got to do to distinguish between B and C is now look at pair number 3. So lead number 82, 207 lead minus 82 protons, and gives us 125 neutrons, and then 213 radium 88 protons, 213 minus 88 is 125 neutrons, so therefore both of those have the same number of neutrons. Thus the answer to which of the pairs do atoms have the same number of neutrons is that pair 2 and pair 3 both have the same number of neutrons for each member of their pair. Confusingly worded question, but one that gives us good practice. Consider the following 4 atoms and state which could be isotopes of each other. So atom 1, 22 protons, atom 2, mass of 40, 22 neutrons, and so on. So anyway, isotopes are the same type of atom, so they've got the same Z, right, the atomic number of protons and electrons, but they have different numbers of neutrons, so that means they have a different mass. So let's go through each of these possibilities and identify as much as we can. So atom 1, 22 protons in its nucleus. So that means that it's a titanium atom. If you look at the periodic table, titanium has an atomic number of 22. Atom 2, mass of 40, has 22 neutrons. Well, 40 minus 22 then is Z, which is the atomic number, which is 18. What atom has an atomic number of 18? The answer is argon. Okay, so the first atom, all we can say is it's a titanium atom. Second atom, we can say it's argon, and we also know its mass of 40, so it's 40 argon. Atom 3, mass of 40, contains 20 protons. Well, straight off we can look at the periodic table and see that the atom that has 20 protons, atomic number of 20, is calcium. So that tells us it's 40 calcium. And finally, atom 4 is an argon atom. So which of these could be isotopes? Well, it's got to be the same type of atom. So therefore atom 2 and atom 4 are both argon atoms. Now, of course, we don't know which particular isotope of argon atom 4 might be, but that doesn't matter because it says which could be isotopes, and the answer is, well, they could be the same atom, or if they've got different masses, then they would be different isotopes. So therefore I'm going to put C, especially as none of the other possible answers make any sense. So now we're happy, I hope, with the relative numbers of protons, neutrons, and electrons, and we've defined isotopes. We now move into the nasty calculations, which are associated with atomic mass. Now, the atomic mass is, of course, the weighted average of all the stable isotopes, and the formula that we use for it is where we say we add up for each isotope. So for Q, we're given that isotope and that isotope, times, I like to use the fraction of the atoms that are that isotope. So in this case here, it's 35% and about 65%, but I would express that as about 0.35 and about 0.65. Okay, so just using this equation, popping in what we know. So do that, and we get that the atomic mass 33.19 AMU. Okay, remember the atomic mass is that weighted average where we take each isotope, multiply it by the fraction that is associated with that isotope, and then add all those up. That's what that funny little sideways M sign means, that Greek capital sigma. Cool, so this is the fairly straightforward example of those. So now we'll get a little bit tougher, told about atomic mass of gallium. So here we're told the atomic mass, 69.72. We're told it has two isotopes, 69 and 71. We're told everything we need to know about the 69 isotope. There's the mass, 68.93. There's the abundance, which of course I will use as a fraction in a minute. And we're asked for the isotopic mass of 71. So we know, of course, the general formula, that weighted average, that atomic mass, is where we take for each isotope the mass times the fraction and add them up. Let's see what we know. We know for isotope 1, which is 69 gallium, we know its mass, 68.93. We know its abundance is 60.11. For isotope 2, we're asked for the isotopic mass, so we can just put that in as X. X, of course, marking the spot or marking what we need to find out. Trouble is, we have a big gaping hole here for the percentage or the fraction of isotope 2. How do we get that? Well, we know that gallium is either gallium 69 or gallium 71. It's either isotope 1 or isotope 2. So therefore the percentage of gallium 71 is 100, because 100% is either 69 or 71, minus the percentage that is 69. Okay, so therefore the percentage of gallium-71, this question mark here, is just 100 minus 60.11, 39.89%. Now I could go ahead and do the calculation with percentages and get nasty big numbers that I then have to divide by 100, or I can go straight in and divide by 100 now to get the fractions. So about 0.6 of gallium is gallium-69, which I'm calling isotope 1. About 0.4 is gallium-71, which is the one we're interested in. So pop everything into the equation. There's the atomic mass, 69.72. Isotope 1, 68.93 times 0.6011. Isotope 2, X that we don't know, times 0.3989. Multiply that out and we get as 41.43. Subtract 41.43 from both sides and we get 0.3989x there. 69.72 minus 41.43. Thus x is 70.92. Answer B. I'm not going to be as long-winded as that in doing some calculations in future, but it's worth stepping through these first ones just so you see how I do the calculations. And then finally, in this particular section, lithium, nastiest type of calculation out, as you will see. Okay, let's go through, blah, blah, blah. Dry cells, storage batteries, high temperature lubricants, excellent information, but we don't really care here. What we care about here starts with it has two naturally occurring isotopes, lithium-6, for which we're given the mass, lithium-7, for which we're given the mass. Lithium has an atomic mass, so we're given the atomic mass. Notice we have not been given any fractions yet. We're asked what is the percent abundance of lithium-6. Well, our weighted average is, of course, for each isotope where we take the mass, and we know the masses, multiply it by the fractions. Well, we don't know the fractions, but we are effectively asked for the fraction of lithium-6. So let's put our little table together. Isotope 1, which is lithium-6, we know the mass. X is the percent abundance or the fraction, so that's fine to have that in as X. Isotope 2, we know the mass, but we don't know its fraction. Well, same idea that we thought of before. Lithium is either lithium-6 or lithium-7. So if the percentage of lithium-6 or isotope 1 is X, the percentage of the other one is 100 minus X, because together they have to add up to 100. So pop that in there. And then, of course, I like dealing with fractions, so I'm going to call X a fraction now, but the total, instead of being 100, is 1. So isotope 2 is 1 minus that X. Pop all that in, so there's the atomic mass, the weighted average, 6.9409. Isotope 1, 6.0151, 6.015121 is its mass, times the fraction X. Isotope 2, mass 7.016003, times its fraction 1 minus X. Expand that out and bring the numbers together. So we got 7.016003 here minus 6.9409. Bring the x's together on the other side. So 7.016x minus 6.0112xx. Make sure you see how that turns into that, and then we're bringing those together. 1.00882x, that's what this side is 0.075103, that's what this side is. So x is equal to 0.07504, but of course we wanted it as a percentage, so we multiply that by 100 and we get 75 or 7.503. So 3 questions in a row associated with the different levels of complexity of using atomic mass is equal to the sum of, for each isotope, the mass of the isotope times the fraction of the atoms that are that isotope.